Hi, and welcome back. Now we're going to talk about electron arrangement in atoms. This is section 5.2. All right, well, that looks kind of difficult to do. What makes an electron configuration of an atom stable? So just like this young woman is kind of upside down and she's got her legs a certain way so she's balanced, we have to worry about the same thing in how and where these electrons are located in the atom. So we have three rules we're going to be talking about initially. When we write what's called the electron configuration, what does configuration mean? Configuration means how we put something together. Okay, so here's a more formal definition of that. So we have three rules. One rule is called the Aufbau, which is a German word, and it means to build up. Bau means to build, and Aufbau to build up. Okay, the Aufbau principle. So we're building up where the electrons are. They're kind of giving them little houses. The Pauli exclusion principle. So we're going to exclude something with that, obviously, and Hund's rule. These are the three things you must know in order to determine where the electrons, in quotes, live, okay, in the atom. So the first thing we're going to do is talk about Aufbau. In the previous section, we talked about the different energy levels. So these ones here basically correspond to the principal quantum number, 1, 2, 3, 4, 5, and 6, for instance. Okay? We see that at the second level, we have 2s and 2p, which makes sense because we talked about that. At the 3 level, we have 3s, 3p, and 3d. 4, we have 4s, 4p, 4d, 4f. And 5s, 5p, 5d, 5f would be up here, it just doesn't go high enough, and so on and so forth. Now, I want to point some things out just looking at this. Look at where the 4s and 3d are. They're almost at the same energy level. That will play a very important role later on. And look at the 4p and 4d. Look at how much higher the 4d is compared to the 5s. It's a little bit higher, and so on and so forth. So that's going to be coming into play with the Aufbau, because what the Aufbau says is that the electrons occupy the lowest energy first. So obviously 1s before 2s, before 2p, before 3s, before 3p. But when we get to the 4s and 3d, the 4s is actually a little lower, so it's going to fill that one before it fills that. So the Aufbau tells us what level fills first. Okay, so usually it's very straightforward if we look like a diagram like this. Okay, I'm also going to draw you another diagram that's really important for the Aufbau that helps me understand it. So, as I said, the Aufbau diagram shows the relative energy levels of various atomic orbitals. Orbitals of greater energy are higher on the diagram. And we have some overlap, which I explained previously. All right, the Pauli exclusion principle says an atomic orbital may only have 2 electrons. We mentioned that earlier in section 1. Oops, sorry. Okay, you can only have 2 electrons. So what we're saying in each of those squares on the previous page, the maximum number of electrons are 2. It's kind of like if you had a house. If each of those are thought of as being a house, you could have 2 people in the house. Okay? Or if you think of the sublevel as a house, you have 1 house on it. Okay? So it's basically 2 people in each room. Now, they have to have the opposites of spin. So the way we show that is we show electrons as arrows. So one will go up and one will go down. So you can't have 2 electrons with what's called the same spin. And spin is a quantum mechanical property of electrons and may be thought of as going clockwise or counterclockwise. We use this as more of an analogy than a truth, but we're just saying that the spins must be different. And as I said, a positive or spin, sometimes we have an up arrow, and a negative one we have a down arrow. So this is what the box looks like. Now Hund's rule is that electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. Another way of saying this is that if you're at the second energy level and you're in the p orbitals, okay? So let me draw those boxes for you. So this is 2p. So 2p would have 3 boxes of the same energy. So as we begin putting electrons in this energy level, I like to draw half ones like this. I'm not going to put another one there. I'm going to put the next one here, because what that does, it lets each of these electrons have as much space as possible. It doesn't have to share the space at all. So when we get to the 4th p electron, then we start sharing the 5th one and the 6th one. But initially, they spread out, okay? So the electrons spread out first before they double up. That's Hund's rule. So there we go. There's the first 3 electrons. So each electron is in one box on its own. And then once we get to the 4th one, then they have to be paired, but they're going according to Pauli exclusion principle, it has to face down because no 2 electrons have the same spin in the same orbital. So you can't have, for instance, I'm going to draw in one of the other boxes. I couldn't do this. Okay, that's not allowed. That's not allowed. No, 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 no. All right, so here's some electron configurations up to sodium, element sodium. And hydrogen has 1 electron in the 1s, so we can make a shorthand. Instead of writing the arrows, we can just write 1s with a superscript of 1 or an exponent of 1. Helium then fills up the other place with, according to the Pauli exclusion principle, it would have 2 electrons in the s sublevel, okay, but it has to face down. So this would be 1s2. Lithium is our third 3 electrons, so we have the same 2 s's, and then we're able to then, according to the off-bow, go to the 2s level. 1s2, 2s1. Let's skip to carbon now. Carbon has a total of 6 electrons. So what we see is we've got the 2 here in the 1s level, the 2 here in the 2s. The next level is our 2p, so we have to spread them out. This one goes here, and we don't have any more. So it would be 1s2, 2s2, 2p6. Nitrogen then fills in the 3rd box, okay? And so it's 1s2, 2s2, 2p3. Oxygen has 8 electrons, all right? So we fill up our 3 boxes like nitrogen, then we start to double up again. So this is 1s2, 2s2, 2p4. Fluorine has 9 electrons, so we have this energy level is filled, sublevel is filled, this sublevel is filled. We've gone 1, 2, 3, 4, 5. Okay. Neon has all of them filled, so we see everything is up and down. And then when we get to sodium, these are all filled. According to off-bow, we go up to the 3s, and then we have 3s1. Okay, so that's how we go through our orbital diagram. So we're doing off-bow, Pauli exclusion principle, and Hund's rule. All 3 help us fill this puzzle. Okay, so as I went over it, the 1s orbital has 2 electrons of opposite spin. 2s also has 2. We're looking at the oxygen. 2s has 2 of the opposite spin. Each of the 2, 3 TP orbitals has 1 electron, and the remaining electron pairs with the first box and so they have an opposite spin. And then I showed you the convenient shorthand, well, an even shorter shorthand than what I showed you there. Writes the energy level and the symbol for every sublevel occupied by an electron. So you indicate the number of electrons that are occupying that sublevel with a superscript. So as I showed you before, 1s1 would be hydrogen, and then for oxygen we have 1s2, 2s2, 2p4. Okay. Add up those superscripts. You get 2, 2, and 4. That's 8. That's the atomic number of the element, which is the number of electrons in the neutral atom. Okay, which one is the correct electron configuration of oxygen? Is it 1s2, 2s2, 2p4? Or why is it not 1s2, 2s2, 2p3, 3s1? Because we're, spreading them out. And I kind of gave you the answer to that. Okay, the 2p orbitals are lower in energy than 3s orbitals, so it has to fill up all the p's before it can move up to the 3s. All right, that's the off-bow principle. Okay, now we're going to have a chance to write electron configurations, and we have phosphorus, which has 15. So all you really have to do is look at the box to do this. You're going to start out at the 1s level and follow the 3 rules and see if we can get there. So let's see what happens. Okay, so first thing we're going to say is, okay, we can put 2 electrons per orbital, and they don't pair up within an energy level if the energy orbitals are equal in energy until each orbital already has 1 electron. Okay, those are the rules that we want to have. So first thing, we're going to look at the off-bow. Our first level is 1s, so we're going to put the 2 electrons in there. That's the first 2, okay, because we go up and then down, because we have to fill up the first before we move to the second. Okay, when we get to the second level, we have s and p's, so we know we're going to basically fill up 1, 2, that's 4 electrons, then p, 1 up, 2 up, 3 up, 1 down, 2 down, 3 down. So we're up to 10. Our next level, energy level, is 3s, so up 1, down, that's 12. And then we get to the 3p, we have 3 orbitals of the same energy, so up, up, and up. All right, that's 15. So that would be the orbital diagram for phosphorus. Now, if we want to make a shorthand, what would we do? We would just take those and take the electrons in each of them and put 2 for the s's, 6 for the filled p's, okay? S is 2, and then we have a partially filled sublevel, so we only have 3 there. We add them up, and we would get 15. Occasionally, things don't happen the way expected. For instance, vanadium has a slightly different off-bow diagram for orbital filling. All right. Vanadium does. Chromium's the next one. It should look one way, but it looks a little bit different, and copper does the same thing. If you look at chromium, we have 3. This is what we would get. Okay. It should be, okay, because we want to, there's a differential here. Sometimes we see this written as 3d5 because that's half filled, and 4s1. 2 half filled are better than, so I would usually see this written this way. Okay. I don't really agree with this. It would be 3d5, 4s1. And the reason for that is that the 4 is not that stable. Half-filled would be really stable. So if we have 2 half-filled sublevels, then this would be, and the energy levels between these two are so close that usually it's 3d5, 4s1. Now this one, a lot of times what we would do with this is we would make this 10 and 1, because that would be a filled level and that would be half filled. So usually we do it that way. Okay. It could be this way, but I don't believe it's true. Okay, so that's the correct configurations. All right, I think what they meant to do here is, if we're going to assign this right, this would be 3D 6 and nothing with the 4S's. I'm not quite sure. Oh, well, I'm sorry. The 4S would have filled up to 2. All right, I see what they did. All right, so this is the correct, I was showing you the correct formation of what it should be. And the reason why we have these exceptions is because half-filled sublevels are more stable than almost half-filled or almost filled, especially when you're talking about D and S electrons. And it only really happens between D and S electrons. Okay, so let's look at the sulfur atom. We'd have to first know what the sulfur atom's atomic number is, and we can find that by looking at the periodic table. So you could just count up all of the superscripts and make sure that's right. So the first one is 4, 8, and 6. That's going to be 14. Is that right? 2, 2, 4. $16. Okay. The next one is 4 and 6 is 10. That's 15. 2, 2, 6. That's 10, and that's 16. And the last one is 2, 2, 6. That's 10, 16, 17, 18. So we have to look at the 2 16s, okay? Because the 2 16s are going to be most likely our answers. So 1s2, 2s2, 2p4, well, that doesn't make sense to me, okay? Because it wouldn't fill that way. B has only got 15 electrons, so it couldn't be that. 1s2, 2s2, 2p6, that's fine. 3s2, that's good. 3p4, that's really good. And the last one has too many, so it must be letter C. Okay. 3 rules. The Aufbau principle. Pauli exclusion principle, the Hund's rule tell you how to find the electron configuration of the atoms. Make sure you know those 3 rules inside out and what they mean. Here's our definitions. Write those down in your notebook. Okay, some more definitions. And that's the end of section 5.2.